Okay, today we're diving into something pretty fundamental, maybe the most fundamental question in science. It's about this fragile thread, the one we call truth.
Ah, the one stretched between the absolute certainty of numbers and the sheer chaos of nature.
Exactly. We're talking about mathematics and physics.
That constant entanglement.
Hmm.
And yeah, often the conflict between them. These are the two big languages we use to try and map out the universe. For centuries, they've been, completely inseparable.
But are they really describing the same thing? That's what we want to explore in this deep dive. We're looking at this really complex relationship.
Right. Are they ultimately pointing towards one single underlying reality?
Or sometimes, especially when you get to the cutting edge, are they just talking past each other?
To really get into that tension, I think we have to start with how they work, their basic methods, because honestly, their foundational approaches are worlds apart.
Okay, let's unpack that starting line. What's mathematics actually doing?
Well, mathematics begins essentially entirely with axioms. These are just self-evident truths we agree on up front.
Given truths.
Given truths, exactly. And from those, it just proceeds through really strict deductive reasoning. It builds these abstract structures, all pure logic. It creates this kind of closed system, totally self-contained, perfectly consistent within itself.
Right. And physics is kind of the opposite, isn't it? It doesn't start inside its own logical box.
Precisely. Physics has to start outside, with observations, with experiments, with measuring the messy, unpredictable natural world.
Okay.
Then it tries to build theories to explain what it sees. And, crucially, to predict new things we haven't seen yet. Physics is grounded in what we can, touch and measure.
So that fundamental difference in where they start, that immediately leads to this sort of philosophical disagreement, right? About what truth even means in each field. It's a big epistemological divide.
Oh, it absolutely is. Think about mathematical truth. Once you prove a theorem within its specific set of axioms, like, say, the Pythagorean theorem, that's it. It's eternally valid.
Doesn't need checking against the real world.
Nope. No empirical check needed. It's what philosophers call a necessary truth. It's true just by virtue of logic. It would still be true even if our universe popped out of existence tomorrow.
Huh. But physical truth,
Mm.
that's never eternal, is it? It always feels kind of
Right.
temporary.
Exactly. Physical truth is always provisional. I mean, Newton's laws felt like absolute truth for 200 years, right?
Yeah.
Until Einstein came along and showed they were approximations.
Right, they needed refinement.
A physical theory is always subject to being refined or maybe even completely replaced if new observations come along that just don't fit the model. Physics deals in what are called contingent truths, statements that just happen to be true, in our specific universe with its specific rules.
Okay, so if mathematical truth is like knowing, I don't know, $1 plus 1 to 2 2 is always true no matter what, then
That-
physical truth is more like knowing the sun will probably rise tomorrow based on past experience.
That's a really good way to put it, yeah. We fully expect the sun to rise because we have overwhelming evidence and models that say it will. But, if the laws of gravity suddenly decided to change tonight,
Then that contingent truth is out the window.
poof, gone.
And this different idea of truth, it leads to these major philosophical camps within math and physics themselves. For mathematicians, you mentioned Platonism versus formalism.
Right. So Platonism is this fascinating idea that mathematics actually exists independently of us, of the human minds. It's like this hidden cosmic blueprint just out there, waiting for us to discover it. The numbers, the structures, they're real entities in some sense.
Okay. And formalism is more down to earth.
Yeah, much more pragmatic. Formalism basically says, look, math is just a really sophisticated game. We invented symbols, we invented rules, and we play this game. It's a beautiful, powerful grammar we built, but that's all it is, an invention.
And meanwhile, the physicists are having a similar kind of argument, right? Realism versus instrumentalism.
Pretty much. Realists will argue that our best theories, like quantum mechanics, for example, are actually describing the real underlying reality. Even the parts we can't directly see or touch, it's a genuine picture of what's under the hood.
But the instrumentalists are like, hold on, if the theory works, if it makes good predictions, who cares if it's real in that deep sense?
That's exactly their position. Instrumentalists view theories primarily as useful tools, calculators, essentially. If the math correctly predicts where the rocket will land or how the transistor will behave, then the theory has done its job. Whether its components, like wave functions or fields, truly mirror some objective reality. Well, that's secondary.
So they're both hunting for truth, but maybe looking in fundamentally different places or valuing different kinds of truth?
Yeah, that's a good way to sum it up.
Okay, but despite that deep philosophical split, the history of science is just packed with these incredible moments where the two languages didn't just align, they sort of fused together perfectly.
Oh, absolutely. The first gigantic one, the one that basically defined the classical era, was the invention of calculus.
Mm.
Newton, he needed a mathematical language to describe things moving continuously through space and time.
Right, how to relate velocity and acceleration and position from one instant to the next.
Exactly. And he developed the math he needed. He called it fluxions, pretty much at the same time he was formulating his laws of motion and universal gravitation. The tool and the theory grew together.
And famously, Leibniz over in Germany was doing the same thing independently.
Right. Creating his version of calculus, using the notation that, frankly, turned out to be much more practical, and it's the one we mostly use today.
Which led to that massive kind of ugly feud between them over who got there first, the calculus clash.
Yeah, it was pretty petty, really. But despite all that academic drama, both their contributions laid the essential mathematical foundation for, well, all of classical physics. It was indispensable.
And that synergy just picked up speed in the 19th century. You have James Clerk Maxwell.
Ah, Maxwell. He took all these separate observations and equations about electricity and magnetism, things people had worked out bit by bit.
And unified them using these incredibly elegant differential equations, vector calculus.
Yes, and what's truly amazing about Maxwell's equations is that the math did more than just describe what was already known. The internal logic of the mathematics itself actually predicted something completely new.
Which was?
When he worked through the solutions, the equation showed there must be waves propagating at a very specific speed. And when he calculated that speed, bang, it was the speed of light.
So the abstract math literally pointed the way to a fundamental physical reality that light is an electromagnetic wave.
Exactly. It was a stunning prediction, born from the structure of the math.
And then, okay, fast forward to Einstein and general relativity. He comes up with this completely radical idea. Gravity isn't a force pulling things, it's the actual curvature of space-time itself.
A mind-bending idea. And to express it mathematically, he needed tools that were way beyond standard geometry.
He needed non-Euclidean geometry, tensor calculus, stuff that pure mathematicians had developed decades earlier.
That's right. People like Bernhard Riemann, working in the abstract, exploring the possibilities of curved spaces with absolutely no thought, zero thought, of applying it to gravity or the cosmos.
Okay, hang on, let me jump in here. Because this is exactly where that famous phrase from Eugene Wigner comes in, isn't it? The unreasonable effectiveness of mathematics in the natural sciences.
That is the absolute core of the mystery, yes. Why should someone like Riemann, just playing with the abstract mathematical concepts about curved surfaces in the mid-19th century, accidentally create the perfect language needed decades later to describe black holes and the expansion of the universe?
It feels spooky, like the math knew something about reality before the physicists did.
It's profoundly puzzling. It really suggests some kind of deep, maybe pre-existing harmony between the structures of human abstract thought and the actual structure of the cosmos. It's, well, unreasonable, like Wigner said.
And the connection goes even deeper than just description, right? I mean, Noether showed something even more profound.
Noether's theorem. You could argue it's one of the most beautiful and powerful insights in all of modern physics. She essentially proved that mathematics doesn't just describe the rules of physics. In a way, it helps generate them.
How does that work?
She showed that for every continuous symmetry you find in a physical system, there's a corresponding conservation law, a direct link.
Okay, can you give us a quick example of that? Like what kind of symmetry links to what law?
Sure, the classic one is time invariance. If the laws of physics work the same way today as they did yesterday and will tomorrow so, the system has symmetry under time translation, then energy must be conserved. It's a mathematical consequence. Or if the laws of physics are the same here as they are, say, on the other side of the galaxy, spatial symmetry, invariance under translation in space.
Then momentum is conserved.
Exactly. The mathematical symmetry directly dictates the physical conservation law. It's an incredibly deep connection. Math isn't just a language. It's revealing the underlying grammar of reality.
Wow. Okay, that sounds like this incredibly tight, unbreakable bond then.
Yeah.
So if math is so effective, Why does this relationship sometimes create so much friction, especially out on the frontiers of research?
Well, because that very elegance, that mathematical formalism, can sometimes be a siren song. It can trick physicists into falling in love with a theory simply because it's beautiful on paper or internally consistent, even if nature doesn't agree.
History's full of mathematically neat ideas that just didn't match reality, right? Like the old idea of the luminiferous ether for light waves.
Exactly. Beautiful concept, mathematically plausible, but experimentally wrong. And the big contemporary example everyone points to, of course, is string theory.
Right, string theory.
It offers this incredibly sophisticated, mathematically elegant framework. It promises to unify quantum mechanics and general relativity, the absolute holy grail for theoretical physics. But, and this is a huge but.
It makes predictions we can't test.
Precisely. It operates at energy scales so ridiculously high that they're essentially impossible to reach with any current technology, or even any technology we can realistically imagine building.
So you have this gorgeous mathematical structure, incredibly consistent internally, but zero experimental verification.
Correct. And critics jump on this. They call it a potential crisis of non-empirical physics. They argue that when you start relying only on mathematical beauty and consistency without the anchor of experimental testing, you risk blurring the line. Is it still physics, or is it becoming more like metaphysics, or maybe a branch of mathematics itself?
A kind of philosophical cathedral built just from equations.
That's a good way to put it. There's also a different kind of trouble that crops up when math uses idealizations that just don't exist in the real world. Math loves perfection, right? Point masses with no size, frictionless surfaces, infinite values.
Things you never actually find in a lab.
Never. And this caused huge problems in the early days of quantum field theory, for example. When physicists tried to calculate fundamental properties of particles, like the mass or charge of an electron, the equations kept blowing up. They kept spitting out infinite answers.
Infinite? How do you even deal with an infinite mass in an experiment?
You don't. It was a clear sign that something was deeply wrong, that the math wasn't quite meshing with physical reality at those scales. So physicists developed these very complex, very clever mathematical techniques called renormalization.
Renormalization, what does that actually do?
It's essentially a sophisticated procedure where you find ways to cancel out these troublesome infinities, often by relating them to the values you actually measure in experiments. You sort of subtract the infinite parts in a mathematically consistent way to get finite, predictable answers.
That sounds a little bit like cheating. Like sweeping the infinite dust under the mathematical rug so the sums come out, right?
Yeah, it has felt that way to some physicists, too.
Mm.
John von Neumann famously said, "You don't understand things, you just get used to them." But look, renormalization is incredibly successful. It leads to the most precise, most accurate predictions in the entire history of science.
Okay, fair enough.
But it does remain a somewhat awkward fix. It highlights that even our most powerful mathematical tools are still an imperfect fit for the gritty details of physical reality. There's still a mismatch we have to paper over.
And then sometimes physics just seems to leap ahead, presenting phenomena that the mathematicians just haven't caught up with yet, like turbulence.
Oh, turbulence is a fantastic example. The chaotic swirling flow of fluids, air, water, whatever, it's absolutely everywhere in nature, from cream in your coffee to weather patterns to galaxies colliding.
But mathematics?
It's largely intractable. We have the basic equations, the Navier-Stokes equations that we think govern it. But finding general analytical solutions for turbulent flow, it's incredibly difficult, maybe impossible in many cases. Chaos theory itself really emerged more from physicists and meteorologists observing strange behaviors in simulations and simple systems.
And the formal mathematics had to kind of scramble to catch up and build a rigorous framework for it later.
Exactly. Nature presented a puzzle that the existing mathematical toolkit wasn't quite ready for.
What's also fascinating, thinking about these limits, is how both fields, math and physics, independently bumped up against their own deep, inherent boundaries to certainty.
Yeah, that's a profound parallel. In mathematics, you have Kurt Gödel's explosive incompleteness theorems from the 1930s.
What did they show, in simple terms?
Essentially, Gödel proved that any mathematical system that's consistent and complex enough to include basic arithmetic must contain true statements that simply cannot be proven within that system. There are mathematical truths that the system itself is incapable of demonstrating. The rules of the game limit what can be known from inside the game.
Wow. Okay. And physics found its own limit.
With Werner Heisenberg's uncertainty principle, this isn't a limit of our measuring tools being clumsy. It's apparently a fundamental feature of reality itself.
What does it limit?
It says you cannot simultaneously know certain pairs of properties of a particle, like its exact position and its exact momentum, with perfect infinite precision. The more precisely you measure one, the less precisely you inherently know the other. Nature itself imposes a fuzziness.
So both fields discovered these fundamental, unavoidable limits on knowledge. One from the internal logic of formal systems, the other from the basic structure of physical reality.
Precisely. Different reasons, but a similar outcome. There are things we fundamentally cannot know with absolute certainty, either through pure logic or through measurement.
Okay, so the challenges we've talked about so far, formalism, infinities, intractability, fundamental limits, they've mostly been internal to this, let's say, math-physics partnership.
Right.
But now there's a new player kind of disrupting the whole game. The rise of computation, especially computational mathematics and AI.
Yeah, this is often called the third paradigm of science, alongside theory and experiment. And it's posing some really deep challenges to the traditional role of mathematics, especially as the sole language of physical explanation.
How so? Because machine learning algorithms can now sift through enormous data sets.
Exactly. From particle physics experiments, climate modeling, material science, you name it.
And they can identify complex patterns and generate these incredibly effective predictive models.
And here's the kicker. They often do this without relying on any explicit mathematical equations derived from first principles,
Yeah.
the way Newton or Maxwell or Einstein did. They function as black box models.
Meaning we don't necessarily know how they're getting the answer.
Often, we don't fully understand the internal logic or the correlations the AI has found. They achieve success purely through massive calculation and sophisticated pattern recognition on the data.
Okay, that immediately throws up a huge epistemological question, doesn't it? If an AI system can predict, say, some complex quantum behavior or how a protein will fold more accurately than our best, most elegant human-derived equations, which one represents the deeper truth?
That's the dilemma. If we start prioritizing predictive accuracy above all else, even above traditional mathematical understanding and explanation, we might be fundamentally redefining what we mean by scientific understanding.
We shift from asking, why does this happen, in terms of underlying mathematical laws,
To simply asking what happens next, based purely on the algorithm's correlation finding power.
I see. So if the AI is just crunching numbers and spitting out predictions, but it can't give us that elegant mathematical story, the why, grounded in symmetries or first principles, we lose something important.
I think many scientists would argue we do. We lose the elegance, sure, but also potentially the insight into causal mechanisms, the kind of understanding that Noether's theorem represents. Mathematics has always provided the narrative structure for physics, the explanatory framework.
And the rise of these incredibly powerful black box predictions threatens to replace that human-readable narrative with maybe just an instruction manual that only the computer truly grasps.
It's an incredibly effective tool, no doubt about it. But it might come at the cost of a certain kind of traditional scientific insight, the kind rooted in mathematical explanation.
Right. Okay, so wrapping this up, we've traced this incredible relationship, the harmony, the synergy.
And the tension, the conflicts.
Yeah. This essential partnership between math and physics is constantly being challenged, whether it's by the sheer abstraction of theories like string theory, or the messy realities of infinities needing renormalization, or maybe even physics outpacing math like with turbulence.
And now, by these powerful new computational methods that sidestep traditional explanation.
And underlying all of this, as you said right at the start, is that core philosophical choice. That question about the nature of mathematics itself.
Is it discovered, meaning it exists independently, maybe as the fundamental structure of reality itself, like the Platonists believe?
Or is it invented just an incredibly sophisticated and useful human tool, a language we created specifically to model the world, like the formalists argue?
And if you lean towards the discovered side, the Platonist view, the implications get really wild really fast.
How so?
Well, the most extreme, most radical version of this Platonist idea comes from the physicist Max Tegmark. He proposed what he calls the mathematical universe hypothesis.
Okay, and that goes way beyond just saying math describes reality.
Wow, far, far beyond.
Yeah.
Tegmark's hypothesis is that physical reality itself fundamentally is a mathematical structure, not just described by mass, but made of math.
Whoa, so everything we see and experience, particles, forces, maybe even consciousness itself, is just the subjective perception, the manifestation of this underlying purely mathematical form.
That's the core idea. If that were true, think about it. The unreasonable effectiveness of mathematics that Wigner puzzled over wouldn't be unreasonable or surprising at all.
It would work perfectly because the universe, at its absolute deepest level, is mathematics.
Right. Math works because math is what reality is made of. It basically dissolves the distinction between physics and mathematics entirely. Every physical law just becomes a mathematical theorem waiting to be uncovered and proven.
Geometry, arithmetic,
Hmm.
they aren't just tools we use to talk about the cosmos.
They are the cosmos.
Okay. That is definitely a provocative thought to end on. So the question we'll leave you, the listener, with is this. If our physical world truly is, at its rock bottom base, a mathematical object, what does that really mean for physics, for our search for understanding, and what does it mean for us, the mathematical structures observing ourselves?
Plenty to mull over there. We hope this deep dive has given you some new perspectives on this fundamental relationship. Until next time.